All right. So, come on, buddy. The naming of ionic compounds, right? Just as a reminder, general reminder. So we figured that, the cations, the metal ions, are always, same as metals, like iron, okay? While the anions is the first syllable of the element, like chlorine, CHOL, and then you add CHOR, and then you add ID, chloride, okay? And we figured that in case we're naming the compounds that are produced by transitional metals and nonmetals, transitional metals like iron, copper, or zinc, we need to specify how many valence electrons are participating in the formation of the compound, like iron 3, chloride, iron 2, chloride, okay? So these are some of the examples, okay? So this will be the formula that we read as iron 2 chloride. We know that chloride always has a valency of 1, so we need 2 chlorides. Does that make sense? Team 2 chloride. Chloride is always a valency of 1, so we've got 2 chlorides for the team with a valency of 2. Okay, does that make sense? And you play from there. So for the exam that I'm going to give you at some point, not next Monday, but at some point, you will have to be able to write down the formula of the compound based on its name and vice versa. Does that make sense? Yes, you can use periodic table as usual. Okay? So that's a little guide for you. Remember that in the name of the compound, cation always comes first. So in the compound like bismuth 3 fluoride, bismuth is the cation and fluoride is the anion. So that basically a guide how you do that. So iron 3 chloride, you would identify the cation, which will be iron, and the anion, which will be chloride. Remember that for chloride, being an anion, the valency is, the number of valence electrons is 7, but it has a valency of 1, so it accepts 1 electron. And for iron, based on the name, the valency is 3. So for 1 iron with a valency of 3, you need 3 chlorides with a valency of 1. And this is how you balance it. So you have 3 positive charges on iron and 3 chlorides, each with 1 single negative charge. Does that make sense? So actually, monoatomic anions usually do not represent any complications, because if we talk about halogens, the members of the 7th group, they're always going to have a charge of -1. Sulfur and oxygen are going to have a charge of -2. Nitrogen and phosphorus are going to have a charge of -3. But the majority of salts that we're going to be dealing with are based by polyatomic anions, formed by polyatomic anions. And what you have to understand is that a polyatomic anion, or sometimes there are cations, polyatomic ions consist of several atoms, like this one, SO4. So it consists of 5 atoms, 1 atom of sulfur and 4 atoms of oxygen. But when we talk about that anion, we consider it a single chemical entity. Does it make sense? So we don't talk how sulfur behaves there, or how oxygen behaves there, we talk how sulfate, that anion, behaves in the reactions that we're looking at. And we can calculate the charges of all atoms in this polyatomic anion. We know that oxygen always has a charge of -2, right? Remember that. Right? Now, the question is, what charge does sulfur have? Well, I can tell you up front that this particular polyatomic anion has an overall charge, like a total charge, 2-. So if you have 4 oxygen, and each oxygen has a negative charge of 2-, how many total negative charges does oxygen? 8. In order to have only 2 negative charges with a whole particle, what should be the charge on the sulfur? 6. +6. No. Does that make sense?
So +6, and then so that sulfur is by itself is +6.
+6. Oxygen by itself is -2. But I told you, we're not looking at sulfur or oxygen separately. We are looking at this whole entity. We are looking at this as the team of 5 atoms. Does that make sense? You understand what I'm saying? These polyatomic ions, they act in the reactions as the single entity. They do not split in sulfur, oxygen, so on and so forth. It's a single chemical entity. Got it? So here are some examples of polyatomic anions. Okay? So for instance, nitrate. Okay? I'm going to kind of nitrate, NO3 minus. This writing right here, NO3 minus, do you see that? That I kind of circled around. It means that the whole entity, 1 atom of nitrogen plus 3 atoms of oxygen, this whole particle has a charge of -1. Now, if it has the charge of -1, what is the charge on nitrogen then? Charge on oxygen is -2. How many oxygens do we have? 3. What's the total negative charge produced by 3 oxygens? -6. Okay? So if the final charge of the particle is -1, what's the charge of nitrogen? +5. Right? So we've got +5 on nitrogen. Okay? 3 oxygens with -2. And overall, the charge is going to be -1. Does that make sense? Now, on the study guide that I will give you, we'll give you a list of polyatomic anions that you absolutely must know. It's going to be shorter than the one that you see there. Okay? But many of those you already know. And as I mentioned before, the best way to eat the elephant is to eat it 1 bite at a time. So that's what we're going to try and do with the polyatomic anions. I'm talking about naming them. Okay? So we're going to start with the anions in which these elements, nitrogen, phosphorus, and sulfur, have the highest possible charge. So let's break down sulfate. SO4 2-. Do you follow me on the screen? It's really important that you follow me on the screen. So how many negative charges does oxygen bring to this anion? 8. What's the total charge of this anion? Always mention negative or positive. -2. So what's going to be the charge of sulfur then? Okay, so we're going to write down the equation. -8 plus 6 equals -2. It all checks out, right? You got it? Go ahead.
So the sulfur is, +6. Where that number coming from?
It's a really good question. Okay, look at your periodic table.
Yes. Sulfur is...
Hold on. Look at your periodic table. How many electrons does it have on the outer shell?
8.
No. 6.
6?
It's in the 6th group.
Oh, okay.
So that's the maximum number of electrons that sulfur can lose. Does that make sense?
Okay.
In the compound like sulfate, sulfur loses all of its electrons. You see what I'm trying to say? All electrons of that atom are going to oxygens. It lost all its electrons. Now let me ask you this. After sulfur lost all of its electrons, how many electrons does it have on the outer shell? Exactly, 8. Because the previous outer shell is gone, basically. Does that make sense? Is it stable? Perfectly stable. Does that make sense? Sometimes these numbers that we write down next to the atoms in polyatomic compounds. So like S or 4. The number 2 minus that we write next to oxygen. And the number 6 plus that we write next to sulfur. These numbers sometimes are referred to as oxidation numbers. Does that make sense? So oxidation numbers refer to either number of electrons that a particular atom accepted, like oxygen, it accepted 2, which gave each atom a negative charge of -2, right? Or lost electrons, like sulfur, which lost all 6, and now has an oxidation number of +6. Does that make sense? Now let me ask you this. Can sulfur lose less than 6? Sure, why not? Okay. There are compounds with sulfur having a charge of +5, +4, +3, +2, even +1. But as a general, it's not even rule of thumb, but it's sort of a trend. If an atom has an even number of valence electrons, it's going to have more frequently even oxidation numbers. Do you understand what I just said? So, okay. So sulfur has even number of valence electrons on its outer shell, 6, right? So one oxidation number that we just learned about is 6. That makes sense? 6 plus. Another one that is really common is 4 plus. Another one that is really common is 2 minus. Those numbers are all even numbers. Do you follow?
What do you mean by all even number?
Even is the number that can be divided by 2. Odd number is the number that cannot be divided by 2. Okay? Without any residue. Okay? So 2, 4, 6, 8, 10, 12, those are even numbers. 1, 3, 5, 7, 9, 11, and so on and so forth are odd numbers. Does that make sense? So let's take a look at some of the anions that are presented in this slide. So we figured out the sulfate. Let's take a look at phosphate. Oxygens, how many of them? 4. Each oxygen has what charge? -2. Because -3 refers to the whole anion. That makes sense? So let's write it down this way. PO4. So oxygen has -2. The total number of negative charges from oxygen are what? -8. The charge of this whole thing is -3. In order to get -3, phosphorus has to have which charge? +5. Which group does phosphorus belong to? Group 5A. How many electrons are on the outer shell? 5. How many electrons did it lose? 5. So it's in the most stable conformation. Does that make sense? It lost all its outer electrons. It's in the perfect position. You got it? Make sense? So if you would look at nitrate, you will see that the same story is for nitrogen here. Nitrogen has an oxidation number of +5, which means nitrogen lost all its electrons. Does that make sense? You can calculate it yourself. It's not too much. So far, we good? Make sense? Clear? So, here's the rule. If the polyatomic anion is formed by an element like sulfur or phosphorus or nitrogen with its highest oxidation number, like 6 for sulfur or 5 for phosphorus and nitrogen, the name of the anion will end with ATE. Sulfate, nitrate, phosphate. Do you follow me?
It's because the oxygen?
Just through. No, not because the oxygen, just through. That's how we name atoms. I told you before, there's a committee. There's an international committee that decides how chemists name things. And one of the decisions, okay, all this sulfur +6, nitrogen +5, phosphorus +5 compounds are going to end with 8, ATE. So sulfate, phosphate, nitrate. Does that make sense? Now, what if you kick it down a notch? And you will have not the sulfur with a charge +6, but the sulfur with a charge +4. So look at this anion here, SO3. What's the charge on each oxygen? -2, total -6 from oxygens, right? Let's write it down. 3. The whole thing is 2-. Oxygens give you 6 negative charges. What should be the charge on sulfur? +4. Can you calculate without writing what will be the charge on the phosphate? Oxygens, how many negative charges do they bring? 6. The total charge of the whole thing is 3-. So phosphorus has a charge of 3+. So not 5 but 3. We kicked it down a notch. And nitrogen is going to have a charge of +3 as well. Absolutely right. Does that make sense? For these types of polyatomic anions. Here's the razor. The name ends with "ite," so end up with sulfite, phosphite, and nitrite. Does that make sense? Good? Questions? Questions? Now, we're going to stop there for a second. And so you need to know these 6, absolutely. That I can promise. Now, there's another set, which if you let me go back for a second, I want to show you. Okay, now look at this. Look at the chlorine. Let me actually circle those so they will be kind of highlighted and you see what I'm focusing at. Do you see the anions for the chlorine? Can you see that? Now, I'm not going to lie to you, that it's kind of screwed up. So look at the bottom one, ClO. What's the total charge of the polyatomic anion? -1. What's the charge of oxygen? -2. So what's the charge of chlorine? 1, +1. Look at the second one, the chloride. What's the charge of chlorine? +3. Look at the chlorate. What's the charge of chlorine? +5. And look at the perchlorate. +7. In which group is chlorine located? Which group? 7th. So how many electrons are in the outer shell? 7. So you see that naming logic here is changed a little bit. And that's one of the worst things that you have to struggle in inorganic chemistry when you start, naming compounds. Because you kind of get used to, if you have an element in the center of that polyatomic anion losing all its electrons, it's going to be 8. Sulfate, phosphate. And here you have chlorine losing all 7, and it's not just 8, it's perchlorate. So probably because they just didn't have enough modifications to the suffixes, so they started to use prefixes. Now, bad news. I'm not teasing you, I'm just telling you. You need to know this 4. Good news. If you know the names for the chlorine, you know the names for bromine and iodine. Because you just replace CHLOR with BROM, right? So instead of, say, chlorate, you have bromate. Instead of perchlorate, you have perbromate. The logic is the same for all halogens. But you need, I'm going to ask you about this 4. Are we clear? That makes sense? Now, some of the exceptions. Cn- is called cyanide. That's a tradition. The name cyanide is basically a combination of 2 letters. C, N, cyan. Does that make sense? By the way, what's the color is cyan? Huh? What? Cyan? C-Y-A-N? Okay, what's the male version of the color cyan? Blue. Told you before that. No, we have like blue, red, green. So cyan. What happens to people that have cyanide intoxication? They suffocate and they turn blue. Okay? And another exception is hydroxide, OH-. So it's basically like oxide but with hydrogen, so that's why hydroxide. Okay? And this too, also no. Now, if you start adding hydrogens, which I'm not going to do to you. I'm just letting you know. So say you have carbonate, CO3 2 minus. Okay. By the way, in the carbonate, what's the charge on carbon? Not 6.
I'm calculating.
Oh, okay. Huh? What's the charge? Huh? Plus 4, exactly.
Yeah.
It's plus 4. In which group is carbon? 4. So it lost all its electrons. It's in the maximum, has a maximum oxidation number. Does that make sense? So, carbonate. If you add H, you get hydrogen carbonate. By the way, since H is always positively charged, you add H and the charge of the anion becomes 1 negative charge less. So it used to be CO3 2 minus. Now it's HCO3 minus. Huh? Got it?
1. Yeah.
Minus 1, yeah. Why it's important? So first of all, in your kitchen, you have the salt that has this chemical formula. Sodium hydrogen carbonate. How do you call it in the kitchen? It's baking soda. Okay? It's your baking soda. What will happen if you, I don't know, make a solution of baking soda and rinse your mouth? Nothing really. You're going to be just fine. Now what if you will get your hands not on the sodium hydrogen carbonate, but on the sodium carbonate like this. You make a solution of this compound. You will try to rinse your mouth with this. This is very, very basic. It's a very strong base that will give you a chemical burn in the mouth. The difference is 1 hydrogen atom. And physiological difference is enormous. Does that make sense? So hydrogen sometimes can give you pretty significant difference in chemical properties. Halogens, the one that we discussed. So know this 4. Okay? So far, let's count how many ions I want you to know. I want you to know sulfate, nitrate, phosphate, right? I want you to know sulfite, phosphite, nitrite. It's another 3. Gives us 6. Cyanide and hydroxide. It's 8. And 4 different polyatomic anions with chloride or chloride. That's 12. And you see they aren't named completely different. So there is some intrinsic logic to the naming. If you remember the order, it's pretty straightforward. Okay? That makes sense? Good? Moving on. So when you write the formula, for instance, you are told to write the formula for magnesium nitrate. Now, it's fine. We can do it ourselves. So let's try to write the formula for magnesium nitrate. First of all, let's just write down all the parts of all the atoms that will be in that compound. So it's going to be magnesium, right? And it's going to be nitrate anion. What's the charge on nitrate anion? -1. So we're going to put like somewhere here, -1. What's the charge of magnesium? It's the element of the second 2A, group 2A, always 2 plus. So, how many NO3 anions do we need to have in this formula? 2. So we put this thing in parentheses. and I was brilliant in writing it the way so I have no space for number 2, but number 2 goes like in this corner, in the right bottom corner, right over here. Okay? Does that make sense? Is that clear? So we did this for several anions already, but we're going to practice it a little bit. And those are 3 steps that you need to do. Okay? So when you're given a name, you start with identification of cation and anion. Then I suggest you just write them plain. No subscripts, nothing. Just plain. Just cation and polyatomic anion next to it. And then you balance the charges. Okay? For instance, here, cation is aluminum. Anion is bicarbonate. Aluminum charge is +3. Bicarbonate charge is -1. So you need 3 bicarbonates to balance the 3 positive charges on the aluminum. Your final formula will look like this. Does that make sense? Now, few rules that you're already familiar with. When you write the formula for polyatomic anions, you always write the cation first. The positively charged cation goes first. Sodium sulfate, calcium bicarbonate, iron 3 phosphate. Does that make sense? And if you write the formula or naming a the ion with a transitional metal, remember about that Roman numeral in parentheses. So, for instance, name the compound like this. So, cobalt, right? I'm going to tell you, CO is cobalt, SO4 is sulfate. So what's the charge on the sulfate? It's balanced, it's all perfect, like no subscripts needed. What's the charge on sulfate? -2. -2. Sulfate, it's -2. So what should be the charge on cobalt? +2. So how should you name it? Cobalt 2 sulfate. Does that make sense? Now, what if you have another compound? For instance, it's copper, yes, and NO3 has -1, right? So if NO3, the whole anion here, the charge of -1, what's the charge on the copper? +1? Yeah. So the name of the compound will be copper 1 nitrate, because copper is a transitional metal. We good? Now this table, I'm going to wrap up the naming. This table gives you some examples, okay, with their role in the human life. And actually, you probably met some of these compounds before. If you ever did contrast X-ray, you were injected with barium sulfate. Many antacids of calcium carbonate, which is also chalk. So if you don't have antacid, just munch on some chalk. Calcium phosphate is used as the calcium supplement in the diet for people who have calcium deficiency. Okay, calcium sulfate is I've heard about gypsum. Now, casts, when you break your arm, the old school molds, that's gypsum. Silver nitrate, okay, this, I'm sorry, bullshit. It is antimicrobial, but it stains the hell out of everything. Nobody uses silver nitrate as the topical antimicrobial. What it is used for, it's used as, I think, a developer in photography. It is. Okay? Yeah. Silver by itself is pretty antimicrobial. Well, sodium bicarbonate, that's the baking soda. Aluminum sulfate. When you use deodorant, antiperspirant, aluminum sulfate is the stuff that blocks the sweat glands and prevents release of sweat. Again, magnesium sulfate is the Epsom salt. That makes sense? So you actually encounter a lot of those ionic compounds in your day-to-day life. So this guide will help you to name ionic compounds. So you need to identify the cation first, say iron, anion second, phosphate. Figure out if that's alkali metal, alkali earth metal, or transitional metal. If it's alkali or alkali earth, it's pretty simple. You just say, I don't know, calcium sulfate. If it's transitional, question?
I was thinking about the test. No.
What were you thinking about the test?
One of the questions on the test, was it alkali earth metals or was it alkali?
Oh, okay. So if it's alkali earth metal like calcium, okay, or alkaline metal like potassium, that's simple. If you have transitional metals like iron, then you need to add this Roman numeral, iron 2 or iron 3. Okay, that's it. And this flow chart gives you an idea how we name. So it's like, you know, yes, no, kind of a flow chart that you can use to name polyatomic, the salts with polyatomic anions. Okay, so we're going to wrap up at this point. I'm going to meet you in the lab. If it's not going to be open in 7 minutes, don't worry. I haven't left anywhere. Just need to collect. What a disappointment. I just have to collect the stuff. And I will grade your exams. So you will see the grade today.